Hello, this is a question I did for probability from a couple of days ago. I can't remember when, but now recording the video. So in part in part A, I guess for this question, I got most of the questions right, but I'd say I'm gonna go over what Gemini said as its answer and then go over my answers, kind of compare it. So in part A, we have this discrete random variable x is uniformly distributed on the set 1 to n. Find e of x and show that variance is distinct. So for this, what Gemini did was um, you have this from 1 to n uniformly distributed. The probability mass function is 1 over n for each of the variables inside that. So hence the expectation would just be the sigma of the values in their probability, which would be 1 over n times sigma of this, right? So then since sigma of that would just be sigma of r is just equal to n times n plus 1. Hence, it's equal to 1 over n times this thing over here, which would be n plus 1 divided by 2. For me, what I did was I just kind of knew that it was this, so I just straight wrote it. Obviously, I think Gemini did a much better job here because it kind of showed you how we kind of derived it, right? Because we have this r times p of x, and then we know that p of x is always 1 over n, so we just have sigma of r. So that's how we got. But essentially, I think it's all right because I got away with it. For variance, we know that the variance formula, what I did was e of x squared minus e of x squared, right? This thing over here. So then I just found each of the things. So yeah, basically Gemini first found this, which would be just be sigma of r squared times p of x, which would be this thing. So we know that this was the given formula, so we just have 1 over n times this thing over here. So we would get this. And then we would just apply what we have from before to the things. So then we would just minus together common factor and we would get this. I basically did the exact same thing. Yeah, so I listed out this. I think it makes more sense that basically I first write out this so that I know, okay, this is how I'm going to approach it. And that's why I define e of x squared. And then this part was already from before, right? So yeah, I did the exact same thing. Yeah, simplified it, combined the things together, and I got this. So yeah, it was done the same way. And then for part B, we're going to ask to find in the first part that we're given x and y are independent, show that this thing holds, right? E of f of x times g of y is equal to e of fx, e of gy. Okay, so yeah, Jim and I wrote this out. We have since x and y are independent, then we can kind of combine the p of e we can kind of take the combined thing and then break it down into two parts, right? P of x equals x, P of y equals y is this equal to this product of the two things. So then we can get that this thing would just be E of f of x, g of y would just be the sigma of x, sigma of f of x, g of y, P of x equals x, y equals y. Um, and then we could just substitute the probabilities, which would just be that from earlier, right? We've broken it down to two parts. So then we can just rearrange it into this and this. It's the sigma of the two things. And hence we would get the expectation. I think I sort of missed out on this part slightly because I should have had two sigmas, but technically, yeah, I should have wrote out like sigma of x, then sigma of y, like that. The two things over here. Should have been like that, but yeah, the ideal is the same. P of x can be broken down, hence I would just have the combined things together, and hence I would have e of x, e of g of y. Yeah, but yeah, for sure, two sigma signs would have been better. In part two, we're just basically asked to show that variance of x plus y is equal to variance of x plus variance of y. What Gemini did is this variance of x plus y. It's going back to its definition. So it's e of x plus y minus e of x plus y squared, right? And then by linearity of expectation, e of x plus is equal to the two things, hence it's equal to this. It kind of expanded the square so that we have this plus 2 times that. And then it said applying the linearity of expectation again, we get that. So then it said talking about the covariance. So the covariance is 0 because we know that um, the things are kind of the same. It's independent. So um, it's just this. I kind of don't like this approach. I feel like it's too algebraically heavy. So what I did instead was I just know that variance of x plus y is equal to variance of x plus variance of y plus 2 covariance of x and y. Since x and y are independent, covariance of x, y is equal to 0. Hence, variance of x plus y is equal to variance of x plus y, right? I think this one is much easier than if I was to have to go through the whole proof from like the definition of variance. Because like I was thinking of using this originally, but essentially this equation doesn't help that much. And this one feels like it would be too much work. So hence like I decided not to go with it. But I think it's definitely doable, and I think I should definitely write it out by hand and try it out myself for sure on this question. And then let's move on to the next part. For part C, we're asked in the first part, a fair die is rolled twice. The rows are independent. Let S1 be the score on the first row, S2 be the score on the second row. Let X equals X plus 1, and Y equals S1 minus S2. It's kind of weird that, okay, yeah, they call it part 1, but it's just the info. So really the question starts on part 2. Calculate the expectation and variances of X and Y. So for part 2, we're first finding expectation. Expectation of x would just be e of s1 plus s2, right? And then the same for y would be s1 minus s2. So by linearity of expectation, we can just break it down into these, and then we just plug in. S1 is expected to be 3.5, 3.5, so we get 7 and 0. Not much to say on that. But yeah, in my work, I think I should have written bilinearity of expectation. Yeah, it's important to write out bilinearity of expectations. That's the case. Yeah. And then in the next part for finding variance, we note that the variance of x is this variance of S1 plus variance of S2 from earlier. So we just sum up the two things and we get that. And then for the variance of y, it's the variance of this, which would have been variance of S1 plus variance of negative S2. Um, but because we can just think of variance of a negative coefficient as something extracted out to be squared, hence it would still be plus of the same thing, so it would still be the same value as before. So for me, yeah, I just did variance of S1, variance of S2, minus 2 covariance of that. So I think would have been better. Like, I think Gemini did a better job here because it just used the fact that okay, yeah, I have variance of negative S2, and then the negative is if I extract it out would be negative 1 squared, so hence it cancels out. I think Gemini did a much better job here than I did. Um, Next part, third part was finding the covariance of XY. So, for the covariance, it should have been covariance is equal to EXY minus EX times EY. And then we know that that's the case. E of XY is equal to this. So then it's finding it that way. Um, I sort of did it as in like kind of like this. I did variance of x plus y is equal to the variance of x plus variance of y plus 2 covariance xy. And I know that x plus y is basically following the same distribution as 2s1 because s1 plus s2 and then plus s1 minus s2, the s2's cancel out, so it's just 2s1. So hence the variance of x plus y would just be the variance of 2 and I have to, because it's squared as earlier, I would have extracted it out, so then I would have gotten this. So then I know that I already know the variance of x and variance of y from earlier, so I just plug those in, and I know that covariance over here has to be 0. Initially, I made the mistake. I forgot to square it, so that was why I kind of got an iffy answer. But I knew that I was definitely wrong because the next part kind of leads me to it, right? Part 4 was determine the values of I and j at which px equals I and py equals j are maximized. Show that x and y are not independent. Okay, so if the covariance was not 0 here, then I know that, like, okay, I don't even need to show this part, right? Because covariance not equal to 0 means that they're not independent. So it means that covariance over here has to be equal to 0. And then you're just talking about, yeah, pairwise what is it called? Independence does not lead to like independence overall. That's the concept tested. So I know that I was definitely wrong at that point because the kind of the way the question was phrased told me that I'm wrong. So how I did this part was basically I just listed it out, right? I'm just trying to find when is my px equals I the maximum and when my py equals j is the maximum. So I just drew out the distribution and I realized, okay, 7 is the maximum because it appeared in every one of them, right? And then the same story with the 0 along the lines. So this is one that's maximized, but I see that there's absolutely no intersection between the two because one is along this diagonal, the other is along the other diagonal, and there's no intersection. So hence px equals 7 and y equals 0 is equal to 0. But I realized that there's no way for something to like one has this probability and one has this probability, right? There's no way the two products could have been the same equal to 0, so it's not independent. So that's kind of how I showed it. I think let me see what Gemini did. Yeah, Gemini did the same thing. You get 1 over 6, 1 over 6, not the same, hence not independent. The same idea. And then for the next part, we have for which values I and j, if any, are the events this and thus independent, justify your answer. For me, how I did this question was, okay, I thought about how I could exactly get it right. So I just listed out what the things were. I know that if py is equal to 5 or -5 on this chart, I realize it's symmetric, so anything over here and here is 1, this is 2, 2, 3, 3, 4, 4, 5, 5, 6. Right? So I know that, okay, yeah, out of 36, it's these numbers for each of the distributions. But then I realized, okay, if um, I have an intersection, right? Um, along. And I realized, okay, this is along one diagonal and this is along the other diagonal. So if there was such an intersection between the two, it must have meant it could only intersect at one spot. So then or at 0 spots. So then hence I would either get the probability is equal to 0 or 1 over 36. But in order to get 1 over 36, my other two probabilities for making it independent would have meant that it has to be something of the form something over 36 times something over 36 is equal to 1 over 36. So then the product of the two things has to be 36 on the numerator to get it to cancel, right? But it's not actually possible because the only way we could get 36 out of this kind of combination, the maximum here is 6 over 36. And that's the only way when we have two of them to be times together to be the case. Anything other than that would be smaller, so it would not be possible. But at the same time, we have already shown that in this case there was no intersection, so it's not possible. Hence, it's just not possible in general. So this was the proof. I think what Jim and I did was the same, I think. Yeah, basically it was just talking about this. I think my proof was slightly better and more intuitive because I kind of drew it out more visually and mapped everything out. So I think it was nicer. Yeah, overall, I think Gemini in this question did a bit more of the kind of relied a bit more on the actual definition of the things, whereas I kind of relied on a bit more of the more useful forms to get the definition. I think the useful forms was definitely nicer, but because it simplified the calculation. But for sure, something I've kind of forgot was that if I have a coefficient in the variance. So let me just actually type it out. Basically, I made this like the slight mistake that I caught later on was the variance of a of x. If a was the coefficient, should have been a squared of variance of x rather than basically a of variance x. I basically took out the a and forgot that I have to square it. So that's something that I definitely should watch out. And it's the same for if I have variance of x1 plus x2, then I should have done, I mean, if it was that, I know that in this case it was equal to x variance of x1 plus variance of x2. And then because of independence, right? Because that was the kind of equation. So then a better way that I would have done it, which should have been for x1 minus x2, would have been variance of x1 plus variance of negative x2, which would have been variance of x1 plus negative 1 squared of variance x2, which would have been variance of x1 plus variance of x2. Yeah, I should have typed it out nicer with LaTeX, but you get the idea. Like basically, those were kind of like the two takeaways I had this for this question. That would have been simpler if I kind of thought about this way, or to watch out for. End it off here.